So number 7 is the first of our 2 advanced challenges. So I'm just taking an example of a couple of them. Like I've mentioned, there is lots and lots of different advanced challenges. And indeed, as I mentioned, please go to the IPEC website, send us an email, and we'll happily look at particular advanced challenges you may have. But for example, I'm just going to take PD location, for example. One challenge that people often face with PD location. You may say to yourself, the PD is largest on this panel or particular cable, so the PD must be here, right? So I've seen the PD on this switchgear panel. This is where it's biggest, so here's the PD. Or I've seen it on this cable. This is where it's biggest, so here's the PD, right? Wrong. How do you locate a PD then? So if we can see a PD on this particular switchgear that's largest, or we can see a PD on many pieces of switchgear on many cables, how do we know where it is across the assets? Mitigation, or solution, if you like, in this case, more appropriately. Firstly, understand the limits of simple magnitude measurement. If you're using, and this is a very common problem we come across, and it's mainly seen on switchgear, but it is applicable for cable as well. Mainly seen on switchgear though. Clients will use handheld equipment to test for PD on different switchgear panels, and on a particular panel, like this one, for example, will have the highest PD, 35 dB maybe. It doesn't mean that the PD is coming from this panel. You've got to appreciate how PD propagates. PD will escape from the gaps in the switchgear panels and travel across the surface. And it can't travel through a panel. It only travels across the surface of panels. In order to find its way to that gap, it may have taken quite a convoluted route, depending on the configuration of the network, depending on the arrangement inside the switchgear, the design of the switchgear, the impedance differences on different surfaces, the resistance on different surfaces. It depends on how this signal is going to travel out and across the surface of the panels. This diagram just emphasizing the PD will, from the PD source, will travel many, many meters away from the PD source. So understand the limits of simple magnitude measurements first. On switchgear, the only way online is to use time of flight, precedence measurement. And by precedence measurement, if, for example, the PD is coming from the switchgear and it's a simplified diagram, using one sensor, the other sensor, the system will automatically tell you this sensor detected it first, this sensor detected it second. If you moved across, you would say this sensor detected first, this sensor detected second. So precedence measurement is a way where you use multiple sensors, measuring the arrival time of the PD signal, and you can narrow it down to the specific quickest exit point or nearest exit point of the PD signal. And that therefore will then give you an indication of where the PD may be coming from, so you can then move to your final phase, which is switching operations. And with a more accurate time of flight system, like the IPEC equipment, 240 picoseconds is the resolution, which works out at about 8 centimeters. So by doing that, you can narrow it down to a particular switchgear panel, and you can most likely narrow it down to a particular component as well, so that you narrow down your switching requirements for your final verification of PD location. And then finally, network configuration. So this is we get a question on this every now and then. It's primarily for cable PD, but it is applicable for switchgear. PD propagates along a cable as if it was a transmission line, and the behavior is dictated by impedance changes. So this is quite a technical problem and quite a technical solution, but we can simplify the impact on our PD measurements. It's important to know that open points on the network will affect the detectability of PD pulses. You need to consider the open and closed status of switches, understand the principles of pulse propagation, ensure PD testing is carried out at a point where the PD will be propagating, will be occurring. And so, for example, if we look at case number 1, the ideal case, we've installed our HFCT to detect PD on our underground cable. We've installed our HFCT at the termination. So around the core in this case, could also be around the earth. In this case, the PD occurs, and at test A, you can detect the PD, and test B, you can detect the PD. Now, if you was to create an open point at switch A, so switch A is now open, switch B is still closed, you will not be able to detect the PD at switch A. And the reason is that in case 1, the impedance difference between these, although there is some small impedance difference between switch A and switch B, generally they're relatively the same. Yeah, there will be some changes, you will get some small reflections, etc. But that high frequency signal traveling across the surface will experience some relatively small difference in impedance, not too much to worry about. However, when switch A is open, essentially it's an infinite impedance here. And so what it means is when the PD signal travels to this point, you get an almost perfect reflection. And that almost perfect reflection essentially cancels out the PD signal. So you can no longer detect it. So although this cable may be on load, although this PD may be occurring, you cannot detect the PD at switch A point. If it was closed, so case number 3, this is where we've got a PD inside the switchgear. Switch A is closed. We will detect the PD at test point A. We'll detect the PD at test point B, because this switchgear PD will be induced onto the cable, travel through to test point B. If the switch is open, again, because of that near infinite impedance, because of the open switch, this PD signal will perfectly reflect at this point and move away from our detection points. So therefore, we can't detect it at switch A anymore. We can't detect it at switch B. Case number 2, as I mentioned before, is probably the most common case. And normally this problem is come across when combining online and offline PD testing. So quite often I've been to site in the past where a customer may conduct an offline PD test followed by an online PD test. And the customer may assume that because this cable is on load, they've just conducted the offline PD test, then they've put this cable back on load for the online test. However, just because it's on load, because we've got this open point here, we can't detect the PD at this point. We need to move to the other end. So this is a very nice example of how the network configuration can affect the PD measurement. Now, I completely appreciate that this is just one example of another advanced consideration of a challenge. And there could be 101 out there. And in fact, there is. And I suppose my conclusions in the next slide touch on how this impacts you a little bit more, or how you can mitigate against this. On the advanced challenges, so on that PD location, on that other example, which was network configuration, there is lots of in-depth information and research out there. And you may have a particular advanced challenge for your network, a particular set of circumstances for your network. Do your research, have a look at the information that's out there. But more importantly, or maybe more easily, just engage with PD experts, share your challenges. And again, this is what I'm going to encourage the output of this presentation to be. If you've got a PD challenge, send IPEC an email and tell them your challenge, and we'll try to solve it for you. That could be a limitation of how to apply technology, a limitation of asset management process, or an improvement required, or it could be a very unique network, your network related issue that you want to engage IPEC with. Ask us. We're happy to engage you, and then ultimately always keep up to date. And the fact that you're on this webinar today means that you've already completed Always Learn step. You're coming back here to pick up some knowledge on application of PD.